Have you thought of this answer for this question? Can big data analytics help us with a systematic procedure to identify spatial and temporal boundaries? Think of a data source and figure out how it can really help you, right? We will have some discussion on that one. We have different data sets. We have discussed Bluetooth, loops, trajectories. Can that really help us to do those boundary identification? The boundaries were like these boundaries when we should like basically identify the patterns in your network, and also which corridors to actually coordinate and when to coordinate, right? Those things, please think. We will discuss that. Now, what I've shown here was, so we can start, right? We can start. We start? Yeah. What actually I have shown here was the boundaries are specified and engineer is defining plans, right? Now, how the engineer is defining the plans? I mean, basically, they do survey. They have a data set with them. They have understanding of that site. So they say, okay, look, I know the demand profile. So first thing, like yesterday we talked about signal timing design, right? Not optimization. You know your demand profile. You know the road geometry definitely. Intersection geometry you know very well. You know the demand profile, that how much demand is expected from different approaches. You define your phases considering whatever is the requirement for that intersection, and then you say I'm going to give a green value for an approach based on the demand it is going to serve. But you don't do that, manually for all of them. There are tools and there are optimization tools that directly people use. Sidra is one of them. In fact, in Australia, it's a standard that every engineer, whoever is doing any signal modeling, has to do the Sidra analysis for the site, which is signalized and unsignalized intersection design and research aid. That's the name of the Sidra software tool. It's a very good software. In fact, I think it's free for academia. With the help of this tool, it's a kind of a simulation. It is actually a simulation, but you are trying to optimize the signal timings in this simulation tool. You have an intersection. You know the intersection geometry. If it is an existing intersection, if an intersection you are planning or designing, you know what geometry you are talking about. You obviously have to do the analysis also whenever you are suggesting any improvement for the intersection. Say I want to add a slip lane, then as a part of the business case, you have to show, okay, basically that slip lane, what impact it can have. So you do your engineering analysis by doing those modifications. If I want to change my signal plans, you do the analysis to show what impact it will have. You can do it for one intersection. You can do it for a corridor. But what you should know is the geometric design for it or your plans for it. Sidra basically considers analytical equations and the simulation. It performs simulation, mesoscopic simulation, to figure out how much for a given phase cycle that you specified, how much is expected delay. So it tries to model those values, and there are different analytical equations by which it can be modeled. I'm not talking about those equations. I will show you some of the equations, but the equations are based on how much, if I give a demand is known to me, signal cycle time is known to me, green time is known to me, what is the delay. So you have an objective function. Let's say the objective function can be to minimize the average delay at the intersection, for example, right? And you have an analytical equation which has the signal timings as your control variables. You just try to optimize it by actually putting various demands inside it. That's one of the summary that you see, optimal signal time analysis results that you see from the Sidra, and you try to basically say, okay, for that one, for example, the optimal signal timings provided by the Sidra is saying, okay, your cycle time should be 120 seconds. For phase A, whatever you have specified your phase A, give 108 seconds, phase B, phase C, and so on, right? So you specify what what proportion of the green split is given to each one of the approach. At least a starting point is given to you. So SIDRA analysis is actually very important in this case. Transit 7F is another one. If you're doing the coordination, there are other tools like max band, etc. There are multiple tools in this space, but the one which is widely used in Australia definitely is SIDRA. And then it also gives you the level of service and the performance on different approaches. Basically, at the end of the day, when you're given a demand, it tells you for that demand, this is optimal signal cycle time, this is optimal green split, and that is expected level of service for that intersection. So the analyst has a starting point. They know this is an expected optimal value to actually play with. Obviously, I have not discussed about various performance measures. Level of service is one of the important performance measures expressed in terms of numbers from A to F. It is again based on different indicators. It can be a delay in this case. It can be other indicators also, and other performance measures also. So that is something you can easily find into your design manual, whatever design is there. So those things we don't have to worry about. Now, once the engineer has done all this job, they have the SIDRA reports, they have studied the site, they have done the fine tuning, they say, okay, this is how I am going to change they have prepared a big report on this for their manager to say, this is the change I am going to do. And then if it is already existing site, they will implement the change. Yes.
Like we have to calculate separate volume.
Yes. You don't want to have you don't want to have a level of service F for any of the approaches. Yes. And basically it is done for the whole also. Yes. Yeah.
So is it executing 7 approaches in intersection?
Sorry?
If in intersection in different 7 approaches, then is it possible to execute this SIDRA software?
Yeah, I mean, this is for this one that I'm showing to you is actually, that is a corridor, right? On that specific corridor, they might have done some optimization, and this is what you get as the result. So it's for the entire one. You tell how much is the demand coming from each of the approaches. You need to know those demand values. How much is a turning how then it is it's an unsynchronized intersection analysis using SIDRA, yes. But here I'm talking about synchronized. Yes. You can do that, yeah. I mean, again, these are what I'm trying to say, that there are tools available to do that part. Yeah. We can do that. I mean, I don't see a reason why you cannot do that. Yeah.
It is almost like signal synchronization.
Yes. But these are offline. So okay, let's say 7 a.m. to 8 a.m. in the morning. You first need to understand for that 7 to 8 a.m. in the morning, how is my demand profile? Means how much vehicles are coming from approach, how many are leaving, what is the turning proportion. So you need to have that OD matrix or the demand profile known to you from 7 to 8, for example, right? That's one. That demand profile might be different for different days. Monday might be different from Tuesday, different days, right? You have to come up with the engineering judgment of what is your design demand profile you're going to use for the site. Then you run your SIDRA for that demand and say, what is my optimal timings? You can think of doing some variations in that demand and done another one. You might get multiple optimal signal plans. And if I look here, different signal cycle time, for example, might have, let's say, average delay, 95% of the back of the queue. Let's say they also have some actually performance index. You have different performance indicators in front of you. You as an engineer must choose, okay, which indicator I am going to focus on, or am I going to consider a weighted combination of this to make a decision for my optimal one. You do an optimal one, similarly, you actually get whatever you get as your those things. This is based on the, I think, based on the delay. So you have to make a decision accordingly. But for that demand for what you have specified, if you have multiple demands, you have to do multiple things. So the one that you have asked, like basically, There are different ways of doing it. One of the ways that long time was proposed by one of my PhD students was, you have, I will open that paper actually and show it to you. You have that was the work done. It was this paper. I was thinking to actually add some slides from here, but didn't manage time, and I thought it might be too much. But you have asked a question, so I will discuss with you. Why? I don't see the full screen here. Why can't I move it around? Maybe I should download it. So what you do is basically you have a for that intersection of that corridor, you know your multiple days demand profile, right? You can think of optimizing your, yeah, that's the one. You can think of optimizing your signal timings for each of the demands. So that was an MCDA approach they propose. So let's like this. Suppose you have a demand profile T1 for that site. You will have some demand pattern. You have an optimal signal time specified for that one. Demand profile 2, you have optimal signal time specified. Different days will have an optimal signal specified for that, right? Then you can say, if I am using my signal optimal signal 1, which I have defined it for demand profile 1 for a day 1, if I run it for other days, what performance do I get? Then you're going to combine them together and say that this is the total performance I have. Because when you have designed your signal for one demand profile, but you have a different variations happening over multiple days. So you say, if I run it that way, what do I get? You then do it for second, third, and so on. Then you will say, I'm going to choose the one which is giving me less variations and which is giving me lower delay. So that's the kind of decision you can make. You can run it for multiple ones and then make a decision. Yeah. So that's actually one approach of actually doing that. But yes, you are using the SIDRA analysis to, or any other tool, any other software tool you might be using to do that optimization. You can even write your own code to actually do that. As part of this work, this is a PhD thesis of Chetrali, who is now working at the Department of Transport and Mains Road as a traffic engineer. She basically developed a cell transmission model, or she modified the, sorry, not developed, she modified the cell transmission model for the intersections, for the different intersection geometry. She added some features on it so that she can simulate the traffic. And later on, I will talk about a cell transmission model also. You can basically make your own simulation tool that can help you to optimize your signal timings. It's a simple optimization problem that you want to minimize the delay, or you want to maximize the throughput, or you want to minimize the number of stops and all those things. SIDRA has a benefit because SIDRA has a lane-based approach that they can. So they have a very detailed simulation done in that space, and there's well standard, very well used. It has a long history of actually R&D. So it's a very I would say stable and actually well accepted tool in the community. So they value a lot. They said, we want to see what is the SIDRA results before you show them anything. Show the SIDRA results because it is well respected in the practice. Because of the maturity of the tool. Now, once you have done that change, Yeah, you have gone and you say, I want to change a plan for this time period. I've done a change today. What will you do next? Will you accept it as it is and just forget about the change? You said, oh, I've done the change, I've done my job, I'm going home, I'm going on holidays. Or what will you do? No, you have deployed it. You are happy with the report. You've done all the analytics. You're happy with the report. You have presented it to the stakeholders. You say, yes, go ahead and change the plan. Now, yes, you have to monitor it.
And we'll see how it actually changes the previous scenario from
Yes. Then how will you compare the previous with the new one?
the same how it shows,
Delay time. Sorry.
how it shows like the LOS and the saturation level.
Okay. So you will try to get those values in the real world, right? Now, on the arterials, like on the motorway, I've shown you, you can draw your space-time plot of your speed versus loop reactor versus time and get a heat map of the speed plot, right? You can compare that without RAM metering, with RAM metering, how much was the improvement. On the arterials, it's not that easy because you don't trust the loop speed at the intersection. You might have some sources like Bluetooth. You might have some sources like here, which is giving you some travel time or travel speed. So you will do the analysis on the data set of your travel time. So let's say today is Thursday and I've changed the signal timing plan from, let's say, 11 to 12. I've done the change today. I know the last Thursday the delay was maybe 15, not the total, the delay was maybe 5 minutes, or 5 is too high, maybe 4 minutes per, on average, per person. I've done the change today. I will go and observe my traffic. Maybe the delay is 3.5 minutes per person, a very high number, but let's say that one. Will you be happy? The last Thursday was this Thursday, so last was 4.5, today is 3.5. Will you be happy by one observation?
Like for intersection, not separately also. Like you'll see how these function.
Yeah, so that has been considered by the way you have defined your safe, by the way you have defined your phases. That has been considered. Okay, but that indicator is also important. It's just whether we have a data set for it or not. But that we have done with the, make sure that when we are defining the phases, I do not let to have a permitted right turn for that approach where I know there are 3 lanes coming or 2 lanes coming. I have done that. I've given sufficient all red time. I've given sufficient yellow time. So that I've not changed. I've only changed the single parameter, cycle time and the green time. So I did an observation last Thursday. I did my change today. I got a new observation. I see the value. Yes, 4.5, 3.5. The delay has gone down. Are we happy?
At least for a
Couple of those days. Yes, one day will not be sufficient. So yes, I will go and do for few more days. I will do some survey for a few more days. I should have done some survey for before. In the past, they used to do that floating cars survey. The surveyor used to do. Somebody used to go and do the survey. I am planning to change my plan on this specific day. Before that, I am going to do some survey. After that, I am going to do the survey. I am going to show that how much the difference is. So you can show, let's on average, in the previous 1 month, the delay was, let's say again 4.5. Now the delay is 3.8. Are you happy on average? Just by looking at the average. Will you be okay with that? Spread, yes. Just one average is not sufficient. You say, look, maybe how's the reliability of the system? Average is fine, but what was the reliability? So what can you do in that case? Obviously, you have to go back and do a survey for a larger time interval before and after. Now, because you have so much of data coming from Bluetooth, here, in telematic, or whatever sources you have, and you have a continuous data for last 1 year, and you can measure the data for next couple of months. So maybe 3 months down the line, you say, okay, I've done that change. I've collected the data for last 3 months. I have data for the previous 3 months. Let's get the entire 3 months data entire 3 months data, look at the average travel time for that time period and see how it has mattered. I can do that. But if I have blindly selected the whole 3 months, what issue I have done? What error am I making? What biasness I have in my system? This is January. The last 3 months might have a different seasonality pattern compared to the next 3 months. It's a complex thing. Maybe the last 3 months, especially in Queensland, there were school holidays. The last 1 month of school holiday, traffic pattern is totally different. Now school has just started, traffic pattern is very different. So you have to consider various aspects. Last 2-3 months there was a heavy rainfall. Now they don't have that much heavy rainfall. There's so many factors impacting it. But if you start considering all the factors, you end up into almost zero sample size. So you have to have a trade-off between the two. But more important is you have to acknowledge the limitation and biasness in your data set, in your analysis. Don't just say that this is a perfect one. Acknowledge that there are biasness in your analysis. So one of the way to do this, which is widely used now in the department, and is something like this: the cumulative probability distribution of your travel time values for that specific location for certain time before and certain time after. Now how do I read it? X-axis is the travel time. This is for one of the roads. Actually this is from the actual analysis, right? On Wembley Road eastbound, they have done some change from 8 to 9 a.m. in the morning. They did the analysis for the previous months, they did some after months. They're using Bluetooth as the data source to do this analysis. So they have Bluetooth scanners installed. They know the travel time for the last couple of months, whatever they have selected. And they get some profiles like this. So x-axis is the travel time, y-axis is the cumulative probability distribution of the travel time. So 8 to 9 a.m. in the morning, the travel time varies from 300 to 500 seconds. What can you say from these plots? Red one means this one is before condition, blue one is after condition. What can you say? How do we read the cumulative plots? Let's first read a cumulative plot. So cumulative probability means how? Means if I look at this one, 0.4, so 40% of your observation on that day had a travel time less than let's say 370, right? 80% of the observation on that day have a travel time less than maybe 430, and obviously 100% had a travel time less than 500 seconds, more or less both of them, right? That's one way of looking at it. So cumulative plot tells a lot about what's happening just in one view. So if you are an engineer and you get this value and you are the one who had done the change, do you think it was a good change, it was a bad change? Does it really satisfy your expectation that you have done a change? Is it really helping you? Sorry? So travel time has increased after, you're saying, or before? What do you mean by offset?
If it was taking even from a graph, if I take any of them, at a given point of time at 350 seconds.
No, yeah, okay, at 350 seconds.
I think the rate is saying something, right? The rate at which the cumulative probability is increasing.
Mm-hmm.
That is giving us an indication that.
Yes, it gives an indication, yes.
The delay time was accelerating very fast.
Mm-hmm. So let's try to draw one cumulative probability diagram. Let's say you are doing observation and you are just getting a travel time of 400 seconds. I've given you 1000 values, travel time is 400 seconds. How does that plot look like? Can you draw that plot? A cumulative probability distribution of a travel time where all the values are 400 seconds. Straight line, right? So you will have something like this, jumping, going and making 100, right? One case, so I will just draw it there. So this might be one of the probability distribution. Everything is not a good line, sorry, but it's 400 seconds, right? So it will be a simple line going up, and this one. Now I give you more data. I say the travel time varies between 350 to 450. Right? On average, it's still 400, or median is still 400. How will the shape look like? It will be slightly tilted like this, right? Tilted. So you will have a 350, 450 means you might have a curve going like this. Both of them will have a same median. I'm hypothetically assuming it, or same average also. So what does that tells you? If everybody is 400, it's a straight line. If spread starts happening, your curve starts tilting. Yeah, your slope starts decreasing. Infinity slope here starts decreasing. So if I look at the slope tells me how much is the spread. More is the, if I said that it was not 350 to 450, it was 300 to 500, you might have a curve like this, right? Slope gradient tells you the spread you have. So steeper the curve, less spread you have. That's fine. Now if I say no, the travel time was not 400, you have all the travel times as 300, then you will have a curve going straight away like this. So the more, obviously if all of them are 300, your average was 300 here. So if your curve is on your left, what is said? It says that I have a less travel time. Does it make sense? So cumulative plot actually tells a lot just by looking at it. I mean, whether it was a cumulative, I mean, there is a cumulative probability plot, but whether it was a cumulative plot for the counts that way I said yesterday, it tells a lot in one go. So from here, my after is on the left, definitely that's what I want, right? Its average is, if I go for the 50th percentile, it was 350, this might be 370. Yes, things have improved on average. Also, the spread has gone down. Although this looks pretty much parallel, but I mean basically it has improved. But if I had another curve going something like this, that's what I would have been more happier. But I'm happy in this case because my travel time has gone down and my spread has also gone down.
This was first the phasing and all that was done on Sidra, and then like on site actual data.
They do the math, yes. So
Then the difference.
no, it was like this. They already had, see, these signals when they are installed or when they are designed, engineering work is done to define the signal timings. Then there is an engineer whose job is to review them after a certain time. Review can be done every 1 year, 2 years, 3 years, depending on how much load that person has. If you are an engineer working in a department, you will be given 1,000 intersections to manage. You will make the decision. Somebody is giving you a phone call. My intersection, I have to wait for 4 minutes. He might give you a phone call and they say, oh, let me have a look on the intersection. Because you have just set it up and now you do not know, and you are sitting in office, you're not driving every day here and there to see for the 24/7 what's happening. It's very hard. So you do not know until somebody gives you a phone call, and quite often somebody gives you a phone call. Then you get a complaint, a formal ticket is launched, you have to act on it, you have to respond back because your responsibility. So then you go and have a look on it. You say, oh, this intersection has some issue. This intersection, the phase was not optimal. The demand pattern has changed. We have to retime the signal. Then you make a case for signal retiming. And you sit down, do the Sidra analysis, get your values, see if I do this, because you get your new demand based on your observation, come up with some optimal, say if I change my signal timings now, I'm happy, I'm going to get better results. I'm not happy, I'm expecting to get a better result. You get an approval from your boss, from your manager, yes, go ahead and change the signal timings. You change the signal timings. But you said, I'm changing it now, but I have to have some period to make an observation of how it's happening. So you will have some period and you will be observing that actually in that time period, because you are the one who is responsible to change it. After a while, you give the data to my team. Let's do the basically you will do it yourself also, not team. Basically, you say let's have a look on it. They will then you will just generate this kind of plot. Couple of weeks back, couple of weeks after, similar type of days. Yes, it looks better. Yes, my after now has better being compared to the before case. Before I was expecting that much delay, after is actually better. So that is the how you decide. Yeah, that actually gives you more confidence. Yes, I mean things that data is telling me things are better. Sometime it might happen things are just messed up because of various reasons. One of the errors which can be done easily. There is a reason why I mentioned the Bluetooth here. If before survey was done using, let's say, floating car based, after it is done using Bluetooth, there are two separate ways of observing. They have their own biasness. I will not trust them. I will not compare them easily because they will have their own noise in the system. If I'm using Bluetooth before and after, I'm actually more confident. So one thing that we recommended to the department and make sure that the source of the data is same before and after, because each source has its own biasness. That's why I wrote Bluetooth here. Yeah. Other is, yes, you have to consider what time periods you are considering before, what time period you are considering after. This is something you make a decision and you discuss with the team. Okay, yes, are we confident? Is that engineering judgment we are making is good enough? Yes, go ahead. You also need to check the quality of the data beforehand. Is the Bluetooth giving me enough samples before and after? Because if something has failed, things have gone from bad to worse, this I won't trust it. So there is a lot of knowledge you have to have beforehand to trust on this. But once you are happy, let's say you are happy with your Bluetooth data set, you are happy with your time period, you get this plot tells you that there is an improvement. Yep.
We can define it as a change, what are the benefits of the change, right?
Mhm.
Given us the change.
Yes.
And let's say it has not actually given us a positive result.
Yeah.
Then we can change the plan.
That's basically, yes, you have to see what can be done. If there's no benefit you have observed, you have to figure out why you have not observed no benefit. So it's always a question of why. Yes, I have done something, but why it's not worked? You should have an answer to this. Not worked because of whatever reason. The reason can be the demand is much high. I cannot do much. Or the reason can be something else. Or your patterns have changed, something else have happened, right? Actually, after COVID, things have changed a lot. Your demand pattern has changed. People are working from home, and the way they are moving is totally different. So that has impacted also your historical profiles that you have defined. So for certain sites, depending on I know Tuesdays are now, at least I feel more congested on Tuesdays than on Mondays or on Fridays. Or even earlier also it was like this, but you feel more because of in certain areas because of the way the pattern has changed. So patterns keeps on changing, and you know that all this optimization was done on a specific pattern, on a specific demand pattern. That's why you have to keep on updating that. I've not talked about the one at the bottom. Here these are different statistics. 95th percentile of the travel time before after. The median that you observe before after, interquartile range you observe before after. I don't know what's happening. Oh, it's because of this, sorry, my bad. IQR slope. IQR slope means the slope of the interquartile range. So in this particular case, before after. Before the slope was percentage per minute, before and after. So my interquartile range has not improved that much. So interquartile range has actually gone actually more on his side. Average slope before after, total buffer time, planning time index. Buffer time index and planning time index are two standard reliability measures. I don't have an equation here, but I will try to open a report and show you what that equation is. But these are standard measures that tells you how much is the reliability of the network. We try to present this in this kind of a plot, going just to show them in one snapshot whether there is an improvement or not, the visual improvement or not, so that it is easy to present that. And this is a tool that has been developed and implemented within that department. It takes the data set, put this one, and they are happy. Yes, they can understand this quite well, and they can easily work on this one.
Criteria to say it is
Mhm.
not a single.
Because different variable represent different things. Median represents one thing, whereas the spread represents the reliability. I can still have a slight improvement in my average performance, but my reliability have gone bad. People value reliability more than, I mean, they value both actually, not more, but reliability has a big impact. If a route has very unreliable traffic, someday it takes me 15 minutes, someday it takes me half an hour, or maybe let's say 45 minutes, then my average travel time is half an hour. Whereas other route always takes me close to 35 minutes to 40 minutes. So that route is more reliable compared to the other one where it spreads all the way from 15 to 45. So reliability plays a very important role also. As we're talking about this one, I will open a, yes, there's a question online. SD. Yes, you can ask the question.
Why is it not audible?
You can you check from the back? Excuse me. We can't hear the person from, or is your mic working all right? Can you please check your mic, please? Or we're not able to hear the audio voice from there. Oh, it's here only? Oh, sorry. Yes.
We can operate. I'm talking now. We're talking. We are unable to hear. I think they're off.
Okay, sorry. You can type the question actually if possible.
I need a break.
Yes, yes, we can hear you now. You can have a break. So we're just trying to open up maybe another PowerPoint if I can find. Yes. Okay, then maybe they can type in and we can just continue. Yeah.
नहीं एक्सेस बंद कर रखा है नहीं यूट्यूब तो once हेलो
Yes, we can hear you.
हेलो
Yeah, that's the report. Yes, we can hear you. Yep. Okay, that's fine. So anyway, I was finding a report for you guys. Somebody asked a question on the performance indicators. There's a lot of performance indicators which are actually out there. Like you can have, this is so hard to, maybe I will just duplicate my screens better. Here we go. So this is a recent work which we have been doing for the government to review, or the department to review various indicators. You have different indicators for efficiency, reliability, surrogate safety indicators, sustainability indicators, even the cost of organization, etc. Somebody asked a question on safety, that do we have to consider the safety also? Yes. When we are looking at the intersection, we have to consider various performance measures with respect to efficiency, reliability, surrogate safety measures, and sustainability. This is important. These are really important ones. And again, the last one is the cost of congestion. There is a modeling that has been done to quantify your excessive delay to the cost attached to the society. And there are models for it. It's not. I mean, they're not. They're very simple empirical models for to actually do that. Yeah. No, it's not here. It should be there, right? I can't. Okay, I'll have.
Chat, just chat.
Could you please explain visualization plot? Which visualization plot are we talking about? Visualization plot. Oh, cumulative plot. Sorry. Yeah. Okay. Yes, I will come to that. So I will definitely come to that. Let me first discuss this one. So there are various performance indicators, like the one you see for efficiency, control delay, section length delay, lane utilization, volume based degree of saturation, volume based degree of saturation with respect to the movement, specific movement. I don't know why these both of them. Oh, this is for the entire intersection, perhaps average. This is for the movement, intersection degree of saturation, and so on. There's a lot of indicators which are out there, and each indicator have their tell you one aspect of the intersection performance. Think of them as a separate lenses. You have a multi-view information about the intersection. So efficiency has its own long list. Similarly, so these are the indicators that, like the way we try to explain what these indicators are. Similarly, you have a travel time reliability has its own long list. It is actually like if you look at the S curve, or the probability or the cumulative probability distribution of your travel time. So that was the curve I was trying to show to you. It's in the shape of an S. The cumulative probability distribution curve tells you straight away, if I look at the 50th percentile, it tells you what's the median. You can get the average. You can even get what is the 85th percentile, what is the 75th percentile. So the probability distribution tells a lot about the reliability of the travel time for that route. Now note, I mentioned that from let's say 11 to 12 a.m. in the morning for that corridor, what was the average travel time over different time intervals for day 1, day 2, day 3, day 4, day 5. So we are talking about day-to-day variations on this one. So it's a whole spread we are talking about. So if you look at, and if you get a travel time every 15 minutes, you have 4 data points for day 1. If you have, let's say, 10 such days, you have 40 data points. So for those 40 data points, you draw the CDF plot. If you do it for the whole month, you have 120, or it depends how long you go, but you get the plot. If you do it every 5 minutes, then in 1 minute you will have how many? 12 data points, and then so on. So you get that distribution accordingly. It just tells how my travel time is varying from one data point with other data point. And because you have done it over multiple days, it tells how the travel time is changing from one day to another day. Now, as a road user, generally, let's say if you're driving, I have to, let's say, go and pick up, let's say, my daughter from a school, and the school finishes at 3 p.m. Every day I might be leaving around 2:50 to 2:30 on that corridor to pick up my kid. Someday it might take me, let's say, 15 minutes, other day it might take me half an hour, some other day it might take me 45 minutes. It's a very unreliable route for me. I don't want to have that kind of system. If it takes 45 minutes, let it be 45 minutes, but be consistent. I don't want to be late there and getting a phone call from the principal that you're not here to pick up the child. Or I don't want to be so early that I'm just wasting my half an hour sitting outside the school where even the policeman is chasing me for that why I'm parking there. So you want to have a reliable system. So this one is trying to tell you how much was the reliability before, how much is the reliability after. So the plot I was showing to you was the S curve was telling you this kind of a reliability. Oh, it is because if you look at two plots, it is comparison. It is just telling you that compared to the previous case, I am actually more reliable. You will never have a perfect straight line like this. I mean, it's almost impossible because of the stochasticity in the system. You can have it on certain let's say public transport routes definitely, but you will have slightly slight because you are on the signal intersection. Depending on the time you hit the intersection, you will easily have one signal cycle worth at least one half of the signal cycle, which is, let's say, not the half of the signal cycle, the red time based delay. So half of the red delay you will anyway observe at the intersection. So if you have multiple intersections, on average you're going to have more delay anyways. But sometimes you are part of the green band, sometimes you're not part of the green band. So that is actually, I hope that answers the question raised by online. It is the S curve we are talking about. It is the probability distribution or cumulative probability distribution, not the probability distribution, cumulative probability distribution of your travel time. This one, I hope in this one we have explained some parameters. Like for example, travel time index is one of the another reliability indicator, which defines the ratio between the mean travel time to the free flow travel time. So generally on the free flow travel time, if it takes me 1 minute to go from, not maybe 10 minutes to go from A to B, but today it takes me 20 minutes, then my travel time indicator is it means that on average it takes me, on a free flow condition it takes me, let's say 10 minutes, but on a congested condition it is taking me 20 minutes. So it means travel time indicator is 2, it's a higher one. So I really need to basically consider that in my mind when I'm driving during the congested condition. It's a ratio of the free flow, the mean to the free flow. Similarly, you have a 95th percentile of the travel time. It is the 95th percentile divided by the free flow travel time. So I mean the minimum travel time you will have basically the free flow one. So it tells you the spread that actually you have in your travel time values, and so on. Buffer time index. This is an interesting index, BT or BTI, BI basically. BT is 95th minus 50th percentile. So 50th percentile minus 95th. So it tells you if you want to be 95% confident of reaching on time, then that's the extra time you have to consider on average. So it defines the difference between the 95th percentile to 50th percentile. So time is also considered, and basically you can also find the index as by dividing it by BTI value. So these are, I mean the lower the buffer time, more reliable you are. So these are the indicators that can be used to show how much benefits you are observing.
It will be different for different modes.
Yes, different modes, yes.
Like all these indicators actually signify just one topic of it. Like
Of reliability, yes.
so,
yeah.
Can it be possible like there might be trade-offs between the indicators themselves?
Ideally not too much. I don't think there will be a significant trade-off. At the end of the day, I think the S curve tells a lot, but yeah, there can be some, like some of them, but all of them are talking about spread. They are talking about spread. One of them is talking about how extreme you are, how less you are, right? So, I mean, the thing is when you are comparing before, after, you're not comparing one indicator against the other. You're comparing what was before, what was after. Yeah. So if before it was like this, after like this, then how much benefit you have obtained. So this is for the, I mean, you can see there's a long list of actually indicators. We have worked with the department to figure out which of the indicators are more important for them that should be considered, all those things. More important, which of the indicators I have a confidence in my estimation with the data I have. That's the more important thing. Do I have data set to estimate those indicators? Maybe not, or maybe yes. For example, surrogate safety measures, a long list is there, and I know a number of you are doing research on the safety here. Break time, break reaction time, gap time, time to break, etc. Long list of surrogate safety measures. They have their own thresholds. Again, if I have a data set, if I can use it to compare how well my signal has behaved with respect to safety. But with the loops, I don't have the data. With the Bluetooth, I don't have a data set. Yes, these are important indicators, but then you need more other data sources to calculate that. Similarly, like if I go to the sustainability indicators, these are in terms of the emissions. How much is the emission in terms of carbon monoxide, NOx, etc. Now, there are models to estimate these ones based on your traffic composition. You can have a microscopic model that can consider the individual vehicle detailed profile, or you can have a mesoscopic model which can use it. For example, like there are some of the models that you see here. Copert, MOVES, these are very standard accepted models that takes into account certain parameters that can be at an aggregated level, or that can be at a disaggregated level. They provide certain features. Again, these are the models that you can do the modeling. Once you have the analysis, you have the data, you can obtain this and also compare how the system has performed with respect to not just delay, but other forms of indicator also. And there is a big discussion within the road agencies that we have just focused only on delay. Then we have to go broad. This whole project is actually to look at this. What are the indicators? What are the performance indicators we have to look at? In fact, initially when I was proposing, well, we just proposed the course 2 years back, right? And I before telling myself maybe I will spend one complete lecture on this, but I thought this is, you can easily find in the literature. This is not something, you know, these are well documented things. So I then moved to something else which is more on the practical experience one. So, but this is what I would have prepared the slides if I would have considered. And but you can see there's a lot of indicators out there. There is a lot of discussion happening in this space regarding what should be the key performance indicators for our road network. How should we measuring the performance of our network? Which indicators to consider? Which indicators I have confidence in? Yes, all the indicators are important, but which one of them I have a confidence in with the data I have at hand. So that's where you have to understand the characteristics of your data set. I might have a data set which has certain biasness into it, and that is not going to help me for that indicator. The indicator is important, but I don't have a data set for it. Safety is a very important part, but I might not have the detailed trajectory for my intersections. So I can do it for the intersections where I have the data. Yes, your question?
So that vehicle operation cost.
Where is the operation cost?
VOC it is there.
Yes.
So it is not vehicle
No. It is emissions. Yeah.
Come only from next year with Euro 7. Euro 7 considers even rubber as a part of
Yeah. So only one model right now is actually giving you, but none of the other models actually straight away give that as an output right now. Yeah. So VOC is the one which you get from actually one of the other models. In actually Aimson, you can generate that actually. We also try to figure out different softwares. Do they have at this point of time? Do they have that model integrated? I mean, these are generally empirical equations based on the vehicle trajectories. You borrow it from the researchers in the environmental space. You actually get that equation. In the case of the simulation, if I'm using Aimson, I know the individual vehicle trajectories, whatever I am simulating. I know the type of vehicle I am simulating. It just tries to use those trajectory values with your empirical model to give you a value at the end. I will never ever trust these values at its own, but I will be happy to compare it one against the other. So relative is the one which I am interested in. Exact value or the absolute value has no meaning for me. So relative is the one you are going to look at. Yeah, because these are anyway empirical equations. You might not have calibrated the equations, or even if you have calibrated, you are performing simulation. This is not the actual world. So before, after, the relative one is the one you can trust. That's for emission. In fact, the another part which actually came quite well when we were having a discussion with the department was cost of congestion. We did not put much details here, but because there are reports within the department. In fact, there was a huge project within the department to model the cost of congestion on the roads. So the modeling that they have done was actually quite simple, but quite powerful. So they say if I have a congestion profile with me, I am expecting certain amount of delay on the road. So it is not the free flow. I know that there will be delay. On average, this corridor might have certain travel time profile. If I am having access to that, that's the cost I'm interested in. And that access can come from various reasons because of incident. Access can come from some other because of the accident, breakdown, weather, whatever it is. That access you generate. So you say on an individual road, amount of time extra that has been spent. You know the composition. So let's say 10% of them were heavy vehicles. Maybe 80% of them were cars. Other 10% of them were public transport. So you know the composition. You also know the value of time. You also know that, okay, maybe this specific type of road users, that's the amount of value of dollar value I'm going to specify. So you know all those things. You consider the in-vehicle like the occupancy rate. The cars might have occupancy of 1.2 or 1.3, whatever you're using, and then you consider the cost accordingly. So all these econometrics figures, you can bring them together. You can just simply do the calculation and get one cost of excessive delay for that corridor because of the congestion, and you sum it up over all the corridors. Certain corridors where I have a heavy vehicle moving, if I delay, let's say 2 corridors having the same amount of delay, but one might have heavy vehicles, other might have like the other type of vehicles. If the value of time is higher for one, then you have more cost lost here compared to other. And so basically there is an empirical modeling behind it, straightforward modeling that gives you a cost. That cost estimate helps you to make a business case that I need to make an improvement on this corridor. Because of this XY reasons, I have so much congestion happening, I would have avoided this if I would have taken intervention. And you always make a business case, say, look, I'm having, let's say, $10 million lost. You're only investing 5 million. And this 10 million will go to 100 million in next 5 years. Invest now. Otherwise this 5 million will be like 50 million down the line. So it's just a business case you have to make. So that's the cost of congestion is a very important one, which we actually brought in the discussion. Other thing, as I've opened this file, I have not discussed any equation for the delay and all those things. I said to you that Sidra might be doing things. There are a number of equations for it. For example, highway capacity manual has its own equation to define the delay, which is delay as a function of progression factors, signal cycle time, and all those things. It's the amount of delay you're observing at the intersection. The first one is the uniform delay, which is straightforward. If you assume a uniform arrival and you have a departure going like this, the area between arrival and departure, the one we discussed yesterday when we talked about the cumulative plots. You have arrival, if you have a departure, the area is the delay. That's first equation. Second one is basically when you have an incremental delay because things are stochastic. Third one is when you have an extra Q, the things have spilled over. So these equations are there, well accepted equations. Some of them are actually, they have the empirical values also inside it. For instance, ACLIC, like the Australian Road Research Board, has its own modified version of the equation. So the equations are the one that you use when you're doing the modeling. And then your level of services are defined accordingly. Different jurisdictions might have a different way to express the level of service. I just showed you one value, but again, these are the standards that you can follow. You don't have to basically, there's no, I would say, rocket science behind it. So these things are there, and again, the pedestrian has his own delay equation. A lot of literature out there where you try to model how much should be the pedestrian delay given the pedestrian arrival and the amount of time you are giving. So that SIDRA output which I have shown to you considered some of these equations. Yeah, in that modeling process. Yeah. I thought not to discuss about this performance, but somebody asked questions. I have to open that file. Any further question on this?
Sorry, this file available in
This is a report we have. The first report is to submit for a project. Down the line we will make it public. Yeah, but you can send me an email, I'll send it to you. Yeah, okay, because this one is a literature review. I should be able to send that to you. It's not a big deal, except for the cost of some of the things which are purely departmental. Because this one also includes the details about how they are calculating right now. Rest all I think is something. It's a detailed literature review on looking at various reports, how it is being done.
going to get in certain place only. If we have this report is complete.
Okay, I will try to have that one in also. Yeah, but more important from this, actually, what we are working on is basically where we are working with the department to, that's the one I think, to actually look at which of these indicators, they are the indicators, try to rank them, how good they are, what data source you have, how much confidence you have in obtaining them, and all those things, because that's what we are heading towards. There's a lot of indicators out there, right? But some of them you will not be able to estimate them because you don't have enough data set. So at the end of the day, you have to figure out which of them are important, which of them are not that much important, or they are telling you the same. Like for example, so many reliability indicators. You don't have to estimate all of them. You only estimate some of them and just move forward. So S curve is a very good example. In one shape, you have all the information. So you don't want to be information overloaded. You want to have the right information to make a decision. And that's where you have to discuss with the practitioners to understand what are their needs and how those indicators are helping to achieve the goals of their organization. Sustainability is a very big, I would say, goal these days. They are focusing on how they can make the system more sustainable. So we need to have indicators, sustainability indicators. We have to figure out how we can measure sustainability. If I have done some improvement, how is it measuring with respect to sustainability? So those indicators have to be considered, have to be shown, yes, there is some improvement from sustainability perspective also. Like we are trying to rate the efficiency parameters, reliability parameters. I mean, this is just a work in progress. This is all based on the discussions with them regarding whether in fact, if you look here, we want to discuss how relevant that indicator is with respect to, which is totally data agnostic. Relevancy with respect to the, to the three aspects we have considered: reliability, sustainability, efficiency, or whatever this, right? In fact, all the list of indicators should be relevant. We have started only the relevant indicators. Representativeness, how well that represent what it should be representing. Then comes your readiness or feasibility. Is it really feasible to estimate that? Yes, I can have a good indicator, but I do not have a data source. I can't estimate that. So we come up with these performance rating, criteria, and then we were having a discussion with them, and it's totally our perception. It's a totally our judgment the way we have done the ranking. There is no science. It's just a discussion with the practitioners to figure out, yes, this is what we think is relevant. This is representative. But obviously, when you go for the readiness and representativeness, you have to have understanding of your data set. And that's why I spent the first day just to explain you the data set. That you know the characteristics of the data, you know the strengths and limitations of the data that can be used to understand whether these things are possible or not. No, different weights. I mean, in terms of relevancy, I think this is the existing file we have. They are everybody should be relevant, but when it comes to representativeness, it is given different weights.
Will that like depend on the expert interview also? Like
Yeah.
how much they are actually.
Yes. This is based on number of workshops with them. This is not just one workshop. I mean, again, this is work in progress. I will not talk about these values. I mean, this is just a work in progress. But at the end of the day, this is going to help us to identify which indicators we should be bringing forward, and we all understand those indicators. The initial objective was study the indicators properly, understand them, document them properly, then you move forward. Okay, that one was. That's what I was trying to tell you. As a traffic engineer, that department has a limited workforce. Maybe if you are an engineer tomorrow joining the agency, you have 100,000 intersections under you to actually monitor. Limited workforce. Budget is limited. You don't have enough budget to just cover everything. And the last one is information overload. Too much information I'm going to give you. Oh yes, okay, that's fine. What do I do? So you have to basically restrict it to some way to define it. Like the S curve is a very good way of showing it. It is straightforward telling yes whether it's making sense or not. So you try to minimize the information into the key information only. Too much information is useless. If I yes, you have multi views, but those multi views should complement each other out. Yeah. This was the discussion we had with them. You have so much data set. The department has like a data from loops, Bluetooth here. This is a well established data set. Established means they have a large database for it. Compass IoT, as I said, that trajectory is emerging. They are now growing more and more. You also have a connected autonomous vehicle data set, which I have not discussed in this series of lectures. DSpark and Near, there are other data sets coming up from your cell phones, right? They are available to the department for certain projects. Each data set has its own characteristics. Like as I discussed, Bluetooth, the loops is the only data that is giving you volume. Loop or a proxy for loop. Let's call a proxy for loop as a camera also, right? Only data which is giving you the volume. None of the other data sets is giving you volume. And volume is very important measure. So there is an importance for this one. Rest all are samples. Now this is the one which is currently the Department of Transport or Mainsort has. You go to some other jurisdiction, you will have something else. US has totally different one. Instead of having a compass, or they have a compass also now there, but some other data source, right? So these, but at the end of the day, these are your trajectories. Here is quite standard. Here is giving you the section speeds only. Here is not giving you the trajectories. In fact, here data is quite huge, and they have their own sections defined. They have their own, let's say 300 meter or 3 meter or 30 meter sections defined, and you have to stitch those sections together to have your travel time or speed profile defined for your study area. So when we use here data for our work, we have to do that work to stitch it together. They give you an average travel time with their own confidence for one section, then other section, and so section. Then you have to map the section for your study corridor and get your values. But they can give you the travel time. They will not give you travel time or speed. They are not giving you trajectories. because of their own privacy concerns that they have. Compass can give you trajectory very, I would say, complementary data, a very good data source that you have from that point of view because it's giving you trajectories. Bluetooth also gives you trajectories, but Bluetooth trajectories are hopping trajectories. They are not a trajectory that you get over the entire corridor. DSpark and Near is basically giving you origin destination. That is not what we have discussed at a large network. They are more from a cell phone based.
Outsource or we are having your own equipment to code this.
Oh no, so this one is like, for example, here is from the hair map. They're buying it. They're aggregators. Here is from the hair map. Compass is totally aggregator. They are just buying it from the car manufacturers, right? And they are growing day by day. DSpark and Near, I'm not sure. I think Near is from the Near map something, right? So I've not worked with these two data sets. I didn't get access to these ones, but they are from your cell phone based. DSpark is the cell phone one. So there are different ways to do the performance measures. I've already discussed the S curve here. There are other measures also, right? I will actually discuss split failure because we have talked about that if I give a green to one approach, green to other approach, can I take some green from one to another? And split failure information is actually a good information to actually do that. Split failure, what is split failure? See, we talked about giving a split. You have your cycle time, you take your expected loss time away, then your amount of green you have on your plate, you split that green to the various phases based on the demand you have. Split failure means the amount of green given to one phase is not sufficient to serve that demand. That's what is meant by split failure. Split failure means the proportion of the total signal cycle length allocated to each traffic movement. This is a signal cycle split which I just mentioned. It's not a failure at this stage. That's a split, right? For example, through phase, let's say 80% goes here, 20% there, the split is 80-20, right? That's a split. Now, let's look at this one. Suppose this is this phase 1, not the phase 2, phase 1. And you have the trajectories. Trajectories are giving you coordinates as they are moving. So you have the trajectories as they are shown, right? Do you see a split failure? This is all good. Do you think you have given sufficient green to serve the demand? Or this is just because I've shown you the trajectories. This is how the vehicles are arriving, right? So I didn't mention x-axis is the time, y-axis is the space. In fact, since last 3 days I'm talking the same thing. So a traffic coming, stopping, going. Second vehicle comes, stops, leaves, so on. Then let's say this is the trajectory of this guy, stops and leaves. So this guy is approaching around the red time. This guy managed to leave the intersection around the green time. This has to stop and then go, and so on. And imagine that this is later half of the red, not just start of the red. Is this a split? I mean, is the split failure? No? Why? These vehicles are leaving, but this vehicle you have to stop. Sorry? Okay. Yes, so it is basically not properly coordinated. As expected, you are going to have some demand coming during the red time, but it's not a split failure. If I have to stop twice, it's a split failure. For example, this case, a vehicle arrives, join the queues, is not able to clear, have to stop again, has to stop more than once at the intersection. That means that split is not having sufficient demand to be served. That's the only thing it is saying, right? It may happen that the intersection is totally over congested. Somebody asked a question during the break. What will happen if I have the demand so high from all the approaches? Then that's an intersection failure. So here, this one is having a, where there's, I mean, I just cut it here, but imagine there's nobody coming during the red time. Perfect coordination. This one is having a lack of coordination, but it's okay. This is what we're expecting. This one, we can say is a split failure. The next guy, this guy has to stop again. Now, can you see one thing? This guy, when he's stopping again, when it reaches, it is basically reaching the red time quite early, right? It's not reaching the red time late in the time period. So this was the definition of the split failure. Is a condition where the green time given to a phase is not enough to service demand. Interestingly, you will not be able to measure the demand. Why did I say that? You will not be able to measure the demand that easy for a given cycle from the stop line loops, because what you measure is whatever has been served. You don't know how much was the queue, right? Let's have a look at another example. Phase 1, this is what has happened. Phase 2, this is what is happening. What can you see here? Sorry? Okay, which one? This one or that one? So there is some unused green. What do you see here? It's a failure. So this is actually for me the split failure, because I have a split which is not able to serve sufficiently. I have another split which has unnecessarily excess green. So if I am able to identify a split failure, I can go and check at the intersection what's happening. Perhaps I have extra green on some other approach which I can take and give it to the first one. So that information is important for you as an engineer, as a traffic engineer there, right? So this is a split failure, and perhaps retiming would reduce the delay. Another example, oh sorry, this is just to show that split failure happened. If you would have retimed, you are able to perhaps make this guy happy. Yeah. Let's look at the example. This is phase 1, phase 2. This is the case you have mentioned. Different approaches. I think you asked, right? Demand is high from all the approaches. Somebody asked this question. Yeah. Sorry, you asked. This is the case. What's happening? Demand is really high. So retiming, just signal split retiming might transfer the delay from A to B. One thing you can definitely check here is the signal cycle time. Perhaps play with the cycle time. It can help you to actually reduce your delay. So cycle time will actually play some role there, because your delay is definitely very high. So if you remember the diagram between cycle time and the delay, it was something like this. So perhaps your cycle time is not maybe too small. Check if you want to increase the cycle time. Other thing you can think of, the phase design itself. I mean, this is a very simple example, but the way you might have designed your phase, you might have to change your phases and see whether you can squeeze some more traffic out of it. So yes, you can do some things still, because when the question was asked, if I have a high demand from all the approaches, what can I do? I said in this case, if your cycle has failed, you can't do much. But I think you can still look at the cycle time. You can still look at your you can still look at the phase design you have. So you can still see what is the optimal solution you might get from there. Yeah, I'm coming to that. Yeah, how do we get it? I mean, obviously, if you have all the trajectories with you, you can easily get that, as I'm showing it to you. All the trajectories, but you might not have all the trajectories. In fact, you will not have all the trajectories. But you can see one thing. I asked you one point. This guy, when he's reaching the red time in the early phases of the red compared to the late phases, right? So if you have a detailed detector data, detailed means a pulse based information. then you can think of looking at your occupancies for the green time and your early red time. Can give you some indicator. But again, the catch here is you need to have a detailed detector data that they call as more of an advanced level detectors, right? Not advanced, they call it more pulse information based detector. They are really very detector which is giving you detailed information. The one that we have at Queensland, the one we are getting from streams right now, I think the best we can get is 2 seconds. They can give you data every 2 seconds, but not the pulse level. But this is more from the restriction of your hardware that you might or your software that you have at the aggregation interval level. It's not easy to change that. Although detectors are just the pulses is what they get. But at the device level itself, when you are extracting the data and sending it to the server, you are doing some calculations there. So that is the bottleneck you have in the kind of information you can get from there. So you will now, if you might not have that in individual pulses, you will have occupancy flow every 2 seconds in some of the systems, whereas other systems you can get the pulses. When I was doing my PhD at EPFL, VS Plus gave me the pulses, which was very noisy, and I spent couple of, I think 1 month to just understand how do I combine them together, or how do I really reduce the noise there. But at right now within streams is every 2 seconds, which is still valuable, which is still good than not to have 2 seconds. Now that's, so you ask question, if I have a trajectory, I can know whether there is spillover or not. If the guy has stopped for more than twice, it's a spillover. If stopped once, it's not a spillover, right? But then again, if I have the trajectory for all the vehicles, if I have a randomly selected trajectory, it can be this one or it can be that one. So sample size will play a role there when you're going to have a random trajectories. But still, if you have those data set accumulated over multiple over multiple days, can give you some good indicator value, some good information, some information better than no information.
Here the device will play, sorry, the detector will play major role. You have multiple trajectories.
No, trajectories, if you these trajectories are from the vehicles, are not from the detectors. Oh, so these are the connected vehicle data. So those cars equipped with the GPS giving you data set, they are the telematics data set, for example. So these are those trajectories I am talking about, GPS based trajectories, not the Bluetooth based trajectories.
Because you have so many cameras,
Then you get it. If you have a camera, you have the whole information, at least for that one. So camera can be a good proxy for the loops, yes. But if you only have the trajectories or loop I am talking about. So split failure, I mean basically just a definition, you're stopping twice. Just a trajectory example like the one, this is, I've already shown you guys earlier also, but I'm just showing it again. These are the trajectories from one of the connected vehicle data from actually city of Brisbane. Very good data source, very complementary data source for us. You can see the way the vehicles are moving. It is the data available for the whole network. Yes, it has its own limitations. If these, for example, if these vehicles are, let's say if the aggregator is only buying the data from BMWs, what will happen? If aggregator right now is a new aggregator in India, is able to get the data only from the high-end cars, what's going to happen? Let's emphasize one, that's good. Yes, what? Sorry? Bias for those vehicles, yes, maybe if it is coming from high-end car who are driving fast, it is some biasness. What else will happen? Yes, it is less sample size because you're not covering a lot of vehicles. Representativeness is not good because your sample is only from one specific sector. What else? representativeness with the sample plus also with respect to space representativeness. I generally might have some high end suburbs, some low end suburbs, some high end area where those traffics are moving compared to the like low socioeconomic areas. So my spread will also not be good, my spatial representativeness will also not be good, right? So there are biasness which you have to acknowledge in your analysis. You should, that's why you should always know what's the source behind the data you are getting. So tomorrow if there is a new aggregator in India starts buying data from the high end cars, you will see a very good sample in Delhi, Bombay, other places, but might not very good sample in some of the emerging cities where those vehicles are not there yet. Yeah. And even in Delhi, very good sample for certain areas where you are having high income group people compared to the low or medium income group people. But this is a very good sample for us for our analysis, better than not having any trajectory. And I'll just show you one of the corridors, and this was done I think 2 or 3 years back. So it is already outdated because the sample grows very fast. We are having more and more, I would say, data coming to these connected vehicles. That is again, in fact, when I was showing you that intersection video from streams was from this intersection. So this is a Compton Road, this one, and I'm going from intersection 1 to intersection 2. That's the stretch I'm looking at, and the one I showed you, all the vehicles moving, I'm going to draw a buffer around this one, a geospatial buffer, only extract the trajectories which are moving in this direction, only those trajectories, right? So, and obviously y-axis is now the space from upstream to downstream is your space taking along the road corridor. X-axis is the time, and for that intersection I've shown you signal red time, green time, red time, green time. I've shown you that one. Now I get my data from that trajectories and I just plotted them. From 6 to 11, the data is from 10th of November 2022. So already 2 years old data, right? So this is what you get. You have a good sample. I mean, within that time period, you are observing some information. But what can you infer from here? Can you get a good split? What do you call? Can you get a good split failure or anything? What can you get from there? Each dot points represent the time, because this is not giving you continuous values. They give you time after certain intervals. It can be 1 second, 10 seconds, 5 seconds. It can be anything, right? So dot points is a dot when I have the data, and the straight line is just interpolation. What inferences can you make from here? This is the y-axis is the reference distance from one point, and the one that we have used was the upstream one. So for example, from here, somewhere here for this, I don't remember from, but somewhere here, and the distance goes along the path, right? So that is the y-axis. So that is the y-axis which is giving, and the x-axis is your time, and this is your first intersection, that's your second intersection, and we are only showing the green time for one of the intersections. I could remove the other slide which zooms in. I will try to see if I can find that one, but what can you see from here? Do you think that this data is good? Can you use it for some of your signal work?
No, sir.
There is online, somebody spoke something? No? Okay.
There are a lot of split failures actually. So
There is a lot of split failures. Okay, how do you find the split failures?
during the red,
I think the voice is breaking. Yeah. Okay, so what you're saying, perhaps during the red time you might have seen number of stops, and from there you're talking about split failure. Okay, good. So there can be a lot of split failures. What else can you see from here? Or their individual trajectories, just to differentiate one from another, randomly selected colors. It was just randomly assigned in MATLAB. We don't have a continuous, yes. Few of them are there, but not all of them, right? Few of them are there. And because he just maybe cut the data points here, but yeah, this might have gone further or have gone left or right, because he just made a buffer along the corridor to actually generate this. Yes, you don't, but we have some of them are really continuous available to us. Yeah. Without stopping, good. So maybe they might just state ones as, yeah. Actually, it looks they cross without stopping. For example, this one data point was here, other one was there. So you might have to look at the average speed. So this one definitely crossed without stopping. This one might have stopped and then left, but because your one data observation was here, other one was there, you did not get the actual, stop and go condition. So you can find the delay easily to certain extent along that intersection. You would have got more information, yeah. No, we just filtered throughout one. I mean, that's what I said. I mean, what the video I showed was everywhere, right? I said that he just draw the buffer along this corridor, buffer, and then extracted only those data points. Because what you had was GPS coordinates like this everywhere, XY coordinates. Because you get the XY trajectories for a specific trajectory. What are the XY coordinates? So he just open a QGIS, define a buffer, figure out whatever data points are they, extract them, and that was a quick analysis. Get those data points, plot them, connect the one which are having the same IDs, so that I can see them as a trajectory. So it can happen this guy arrived when maybe it might have left. That's why you don't see it further down. Or this guy might be coming from some other approach. Therefore, you see this point, but you do not see the other approach or from where they entered. So these might be the one which have entered from the side, or these are the one which are going through. Well, it all depends how you present the data. So this was a quick presentation, but it's important for you to understand how it was presented. I won't say it's a perfect presentation. I will see if I am able to show the dashboard tomorrow, because now we are building the dashboard on this one where you can select and get all the information. But yeah, you can actually get a lot more information. Our sample is much higher, but this for the teaching purpose I'm just using this one. So this one thing which nobody had mentioned, or to a certain extent you have mentioned, was data was at certain points, right? So one important thing you have to consider for the analysis is how frequent you are getting the data set. Sample, well, you mentioned sample is important, how much sample size you have and how frequent you are getting.
The points are not continuous.
Mm-hmm.
So I can say if less points are there, the vehicle is having more speed.
The points are not continuous. Okay. Yeah. Yes, it can happen that way. Other thing is they are from different sources. The source data varies from 1 second to 10 seconds. I can have a source A giving data every second. I can have a source B giving data every 5 seconds. So it is not from one source. So that's why some of them have less data points in this space, some of them have high. But yeah, speed is going to play an important role. If speed is high, even if I'm giving every 5 seconds, I might be hopping a lot. So those things are there. So you have to understand what are the characteristics of your data set, how frequent you are getting, how much is the penetration rate, and obviously how much confidence you have in the data. But yes, this can give you this data set. In fact, I will actually try to find that slide. What Tamojit did was he zoomed in, and basically when you're observing a point here, a point there, he tried to use the shock wave theory to further define the trajectory of the vehicle. So you can actually add some further analytics on this to find to shape how the trajectory might look like. But even before jumping there, you can easily get the travel time, you can easily get the speed profiles, and if you have a slightly better frequency, you can easily know how much is the which of these trajectories are facing more than one stop at the intersection. If they are facing more than one stop at the intersection, then it's highly likely that the intersection is having, or that approach, this approach, not intersection, this approach is having a split failure. So trajectories can give you information about the split failure, but not alone. I mean, alone means not just one time interval. You might like to, in this case, what you do is you study that time interval for large number of periods. So let's say from 11 to 12, I've done the change in my signal timing. So this is same timing of interest to me. I am observing data for multiple days beforehand. I get my trajectories, they are randomly selected trajectories. Some of them may not be stopping, some of them may be stopping. So if you go for the last time interval before, you can figure out what proportion of those trajectories were having a split failure. If you figure that out, because then you have randomly selected them, you can show the likelihood of a split failure on that approach. So if I go back to this one, suppose this is day 1. I'm randomly selecting one. I might have selected this guy. Day 2, I have a similar profile. I might select that guy. Day 3, I might select someone else. So if you do it over the last time interval and this phase is having a split failure, it's likely you are going to get observations. And then you will say, okay, X percentage of my trajectories have shown a split failure. So the likelihood of split failure there is whatever it is. But it has been a last time interval and you need to have a sufficient sample size or sufficient penetration rate, which can be 5%. If you have 5%, I think you are really happy. What proportion of your trajectories are, or what proportion of your vehicles are represented as a trajectories? So in this diagram, penetration rate is very low, maybe 1 or 2%, right? But I think it is growing. It might be now 5 to 10%. It can happen, right? So penetration rate is, let's say if I have all the trajectories here, or if I go at this one, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you only observe one trajectory, is 10%. Yes, we should have. If the penetration rate is less, you will not have a confidence. I'm saying 1 on average. So it can happen on this cycle you have nothing. Next cycle you pick up 2. Third cycle you have nothing. Fourth you have nothing. Fifth you again have 2. So on average basically you might have a 10%. So trajectory data is actually very valuable. It is a complementary data set that you will get and can help you to get a penetration rate. You can stretch yourself. Yeah. We can have 2 minutes break before we start next. Is it too much information overload? Yes or no? Yes, sir? Okay. I should then we can have 5 minutes break then. But there's no point for me to speak if you don't understand. Are you understanding? Okay. Okay. He don't want to take a rest. Okay, let's go. Which one? Okay. What do you want to? Oh. No. What? What did I start today? Okay, I will start. Yeah, I will just go there. I think it's okay. So from where did you start? Others can take a break, please. Please go ahead and stretch yourself, please. At least stand. At least stand, because you have been sitting for almost 2 hours now. Design process, right? Okay. And when did you start?
Meta-heuristic approach for design.
Sorry? Meta-heuristic approach for design. So I started with this slide today. Yeah. I mean, this is something we discussed yesterday, right? There are actually various steps involved in your signal design, and obviously you go from you have to design your phase. So what actually you missed was actually the whole phase design concept, that there are different ways to actually design the phases. That's one thing you missed. I think second thing you missed was that when you are trying to, so let me have a look what, so let me just quickly go through how you can design the phases. So phase design is actually a very important part. We discussed about 3 ways of designing the phase. One of them was a stage based control, second was a NEMA, third one was a group based control. Phase based, you already know that, right? You fix your groups together and you define the phase. That is the phase base. Yeah. NEMA ring and barrier is something which I introduced. It is, you have 2 rings. In this example, you can have more than 2 also. You have an upper ring and a lower ring, ring 1 and ring 2. For you define your phases, the concept here is the way you have defined the phases is, and you have a barrier, that all the phases of the same ring, they are not compatible with each other. They should never occur together in general, right? And for a given portion of the barrier, the phases can work in parallel. So let's say phase 1 can easily go with phase 5. Phase 1 can also go with phase 6. Phase 2 can go with 5, phase 2 can go with phase 6. But phase 1 cannot go with 7 or 8, and similarly 3 and 4 cannot go with 5 and 6. That is because if that's what you are looking at, then this is going to help give you more flexibility in the way you're going to design the phases. For example, fixed approach was this. In this case, if you would have, if you cut your, well, these 2 rings can work independent of each other. If you make an early cut here, the combinations you are going to get in the display green is phase 1 with this phase 1 with that phase also, then phase 2 with this phase, and so on. You get multiple combinations, right? Or if you make a slightly different change, you get a different combination. So you are getting different combinations by giving a ring and barrier. So it's just giving more degree of flexibility for an engineer to control it, right? But then I said, no, this thing can also be done in a phase-based approach also. The way you define your phases, the way you define your sequences. And there are different sequences I considered in this one. And one of the important sequences I raised was a diamond overlap sequence, where you have this combination A, you can have a B, either as B1 or B2, you can have C, D, E, and F. So you can have a combi going from A to B1 to C to D to F. You can skip E, or you can skip B. You can go from A to C. You can have multiple combinations. So by designing your, again, this is something dependent on the geometry of the intersection. You have to be intelligent, or you have to be smart enough to figure out for your intersection what design you are looking at. So you can design it accordingly. Yeah, that is something you missed. Then I discuss about a detail about the phases. So then I talked about the third level of complexity. The third extra degree of freedom. I said you can have different groups or the movements which are grouped together, make them independent of each other. You have a pool, you can select anybody from the pool and let them run as long as they are compatible. They are allowed to go together. You don't need to have the ring or barrier or the phase structure. It's an extra degree of flexibility. The thing I said here was, previous case you have a conflict, I didn't talk conflict matrix to you. You have a conflict matrix, which means that wherever you have a cross, those things should never ever go together, right? And that conflict matrix is the one defining those your ring and barrier or your phase sequence. In this case, you have an intergreen matrix. What it says that I can start with K1, I am finishing at K1. If I have to start K3, I should have a 4 second of intergreen. So I can select, like I'm working on K1, I am working on K1 and K2. I can finish K1 off. I can start K6 after 6 seconds. But if K6 is compatible with K2, it will hardly matter. So you have all the flexibility with you. You're okay with this? Because you can say K1, K2, K5, K6. So K1 and K2 can go together, they are working. Now K1 demand is over and you have to cut off K1. You can select K6 because K6 is and you can still let K2 run, but if you select K6, it has to start after 6 seconds only. So that's the way you can make the selection. But then when I was presenting this, I said, somebody asked a question, how does it really work? So I went to one of my students' work to explain that, how it works. Like he's working on max pressure based traffic signal control. So he has some control logic to make a selection. Just imagine here he has a logic to make a selection. What he has done is, for each movement, he has defined all the possible compatible movements with it, right? If I have selected northbound through, I can select any of these three. If I have selected northbound left, I can select any of the other ones. So he has done that selection. So he has that with him, right? So his algorithm is saying that I have a function where I'm going to select a specific approach based on some values. And I make my decision, I'm going to select, let's say, northbound left. So that is my decision to select northbound left. But then I'm also going to check, I'm not just going to run northbound left. I'm going to run other approaches also, which are compatible with it. But I have a pool to select. I'm going to select the one which is having, let's say, the maximum amount of expected queue length or delay or whatever it is, right? I will select one from there and I will let it run with that. Now, when I have, in fact, somebody else later on asked me a question during the break that by doing so, it can happen that you are just selecting few of them always. Some of them are left behind. So that was addressed in this case by making sure that your primary selection is done once only. Primary can be selected again, but will never be selected as a primary again. So that will make sure that everybody is selected before you select that one as a primary again. So you add some constraints into it. So that's the way you can actually control. Yeah, but then I asked a question to them, for Indian condition, what challenges you're going to face if you're going to apply this kind of approach. लंच हो गया इनका? Yes, you have a question? Suprabit Datta?
Yes, sir. Actually wanted to know that the visualization improvement plot, actually the
Okay.
description of the visualization improvement plot for the travel time reliability plot you showed, no? So
Yeah.
that
Yes, what is your question?
yeah, I wanted to know about like, can you please briefly explain about the visualization improvement plot in the CDF plot of the travel time reliability you showed, no? Before and after
Yes. Okay.
designing of signals. That portion I wanted to know.
I will just open that plot where it is.
Yeah, that plot
Yes,
was.
yes. I will
Yeah.
just before after is. Here we go. That's the
Yeah,
one, right?
this one. Yeah, the
So let me. So
just
please
next
be
to the
online.
table.
I will ask you few questions. Please answer that to me. Yeah. So
Yes, sir.
how do I read this one? X-axis is the time, or the travel time. So travel time along the corridor. Okay.
Yes, sir.
Y-axis is the cumulative probability distribution values for that travel time. So it's like this. I have observed my travel times for the last 1 month for that specific corridor. I might have observed, let's say every 5 minutes for 1 hour, I have 12 data points. I might have observed it for last, let's say 30 days. So I have 12 multiplied by 30, that many data points with me. And this is the cumulative distribution plot I have from there. So what it tells me is that, let's say the before plot is the red one, my let's say 60% of my data points has a travel time less than 400 seconds. So 60% of my observations before had a travel time less than 400 seconds. Maybe 50% has a travel time less than 340 seconds. Are you fine with that?
Yeah, I'm fine with
Yeah.
that. Yeah.
What about the blue one? So blue one is having more or less travel time for the 60% of the case.
It is having lesser.
Lesser. So
Lesser.
the more the plot is towards the left, lesser is my average travel time and the median travel time, right? Are you okay with that?
Yeah, yeah.
Yeah. So if my plot has shifted towards left, it means that my travel time has decreased. So if before it was on the right, after it is on the left, it means that my average travel time has decreased.
Okay.
Yeah. Now other thing is the slope of the plot. If
Okay.
the slope is basically very steep, it means that most of the data points are concentrated around the same, around one value, right?
Yes, yes.
So
You're talking about the central tendency. Yeah.
yeah.
Yes, sir.
So if the slope is steep,
Yeah.
I have less deviation. So it
Yes.
means that a steeper slope is giving me more confidence in my travel time. So my reliability is better.
Yes, yes, yes.
Now that's the only concept which is there. So if I have, let's say, another plot, let's say I have a S curve going something like this, and I have another S curve going like that. For instance, I have two S curves. Let's say this one was before, this one is after. This is my travel time and this is my cumulative probability values, right?
Yes, sir.
What can you say here? Has the system gone better or worse?
It has gone better actually because
So before, so the first one is before, second one is after. Yes. So
no, it has gone. It has gone worse. I think.
Okay. Why?
So because after the travel time means it is shifting towards there's as the cumulative probability is advancing.
Yeah.
Of travel time data points, so the travel time is a little bit decreasing with respect to the before implementation of the.
So if I look at, let's say, this is let's say this is the 50th percentile. I had, let's say, a travel time of 300 before. Now I have a travel time of 400. So my travel time has increased afterwards, right?
Yeah, it has increased. So
Yeah,
it has
increased.
worsened.
Yeah.
Yeah.
And moreover, the slope has also gone down. So most of my data points were concentrated around 300. Now they are concentrated all the way from 300 to 500. So I have more spread. I have less reliability in the system.
Okay.
So higher the, I mean, in this example, there was not much difference in terms of reliability because the slope looks quite parallel. But if my slope would have gone more, I would say steep, I would say I'm actually having a more reliable travel time compared to the previous case.
Okay.
But having said that, if I make another plot, let's say this is the one I had before, and this is the one I have now. So this is before, and this is after.
This is
So obviously, the before you had less travel time, after you had more travel time has gone bad. But afterwards, you have almost everybody having the same. So your reliability looks better. But that is not what you're only looking at. You look at the comparison of the two. Afterwards, that before, let's say somebody might be traveling for half an hour, somebody might be traveling for 1 hour. Now everybody is
Yes, sir.
traveling for 1.5 hours. So you're not happy with that
Yes.
one, right? It's more reliable,
Yeah.
things are really bad, but it's not what you're aiming for. So you have to look at the
Okay.
plot and make your own, like make the judgment accordingly.
Okay. Okay.
But does that make sense?
Yes, sir. It is making sense.
Thanks for asking this question.
Yeah.
Yeah.
Thank you, sir.
Thank you. But one thing I like in teaching, these things, by the way, I'm teaching first time. This is not what I've taught in the past. They're from my research, but not taught them. So when you ask questions, that helps me for future teaching. That I might be able to explain them in a different manner. So that's why I do not have slides. Like in the case of traffic flow theory data, I have taught in the class. I have slides. Here I don't have slides. I have my research papers, research reports, which I'm just bringing to the classroom. More questions? I think we should be taking then a lunch break now before starting, right? But we can still ask questions right now. Do not straight away go for lunch break. We have break from 1 to 2. Try to come as early as possible. If you come by before 1:45, can you be back by 1:45? You can ask me questions at that time, right? We will start at 2 only. We not start at 1:45, but we will try to ask more questions, right?
One question
Yeah.
think about in the break is it useful in Indian
Mm-hmm.
foundations?
Yeah.
Can you bring up the question?
Yeah. So I have asked 2 questions actually. Yeah. So one question was based on whatever learning you are having or whatever I have discussed for traffic signals. What you think should be the research or work to be done so that you can implement some of the things or you can do something for traffic signal control in the Indian condition. Don't worry about traffic data. I mean, imagine data will be given to you. Do not worry about the side friction at the intersection. Think about you are able to enforce things, but what kind of work you have to do so that you can have more better traffic signal optimization done or have a proper design done. So you can think of whatever way you can get the data set. You have the money to actually buy the cameras, or you have the money to actually buy. Or tomorrow there's a new aggregator in the market who is getting the data from the third parties and happy to share it with you. Yeah, or the government is buying the data from the third party, happy to share with you. Make those hypotheses. That was the first question. Second was, I've shown you that you have to like the process to optimize the signal time or to retime signal timings is a very tedious work. You have to define the time periods for which you have to adjust the signals. You have to define the demand and optimization to be done. You have so much data sets. We have discussed at least in Australian conditions, Bluetooth, loops, trajectories that is available to you. How you can properly leverage that opportunity to better, or what work to be done so that you can better define those boundaries and you can better optimize the signals. You have SIDRA with you, you have the entire data set with you. What you think you can do based on that data set to help the agencies so that they can make more informed decision in a structured manner, or they have more confidence in it. So these are the 2 questions I asked. So first one was purely on Indian conditions. Second one was whatever learning you have. If you are the consultant, let's say you actually get a job in one of the consulting firms, and the department has asked you this question, what will be your response to them? Yeah. Think about it. Oh, later. No. It's not nice. It's already 1 o'clock. I don't want to hold you guys. I want to start at 2. Yeah.